as I said, let's get started with our Atwood Pulley demo and go from there.
Atwood Pulley. That means, and I have a discussion, if this is a 200-gram bass and it's at rest, that means that gravity is pulling down 2 newtons on that weight. And I asked them, what is the tension in the string? And what do you think, if there are a 2 Newton weight on this side and a 2 Newton weight on this side, what's the misconception that they're going to say is the tension in the string? 4. They're going to say 4. There has to be 4 newtons in the string.
Love adding.
Yeah, so they're like, oh, well, there's 4 newtons. You're pulling 2 on one side and 2 on the other. If you wanted to do vernier stuff, you could actually put a force probe in here, or a force scale, which we've got over here, in there and see and have them measure. There's only 2 newtons of tension. So think of it this way. If there were 4 newtons of tension, yeah, this has got 2 newtons down, it would have 4 newtons up. This would be accelerating upward. If this had 2 newtons down, 4 newtons up, this would be accelerating upward. These things would be flying to the ceiling, which they're not doing. So now, this is actually a Newton's first law demonstration. I move it up, and now...
Pause, we have a question. Yes, what? You're answering a question, another question. Okay, maybe that was to someone else. Okay, let's continue.
Now they're not even, and this is basically a massless string. It's so light. And I asked them, I'm going to let it go in a moment. What's going to happen? And they have no idea. A lot of kids will think of it like water. That, oh, Mr. Sharp's going to find its level. It's going to go to here. Some kids are going to say, oh, well, it's going to start to fall, but then it's going to have speed, so it's going to keep going, and it's going to go all the way down to the floor. Some kids say it's not going to move at all. And so my point when I have it up here, and I'm tricking them because I'm holding it, is that the forces are still balanced. It's still in equilibrium. Objects without a net force want to stay at rest, or move in a straight line at constant velocity. So when I let it go, what is it going to do? Nothing. And it just stays there. And it freaks them out.
Yeah.
Shouldn't this fall?
Yeah.
What would I have to do to make it fall? You could give it an initial velocity, which means the forces are still balanced. So what should we say it do? Move at a nice constant speed. And it's very cool. I've read a lot of research that over and over says, because this is our habit as teachers, and I'm guilty of this all the time. You're going to make that misconception. Things don't need a force to move at a constant velocity. Don't make that misconception. That's not enough. You need to show them something that like actually destroys it, you know, and makes them like, oh wow, I didn't understand what's going on. That's why the trick for me is I ask them to predict before I show them the demo. So when I'm here, what happens? And they tell me what they thought was going to happen, and then they're forced to recognize they were wrong, and that's big. The other way to make this thing accelerate would be to make the masses different. So you could take a small paper clip now and put it on this one, and you would see it accelerate. And I could put in 3 paper clips, and I'd see it accelerate more. And because now the tensions are not, well, the tension would be equal if we're talking about a massive string. The masses on either side, the forces would not be equal.
Now, how would you?
All right, pretty cool question. Hopefully you found that visually all right. Yeah, there was 2, oh, your screen. So yeah, there were 2 masses, one on each side for the Atwood pulley to be Atwoody. You know, there's always 2 or more masses. So yeah, I just wanted to do that to show a demonstration of what that pulley looks like, you know, visually. We can kind of imagine it, but it's nice if we can see it. Okay, so let's get to question 32 of our homework and 69, and then after that, around 150, we'll go to our quiz. Any questions on the demonstration? Just standard. Just wanted to kind of show that to you.
Um, can you draw like the pulley itself with the weights on?
Cause I didn't get a good picture of it like in my mind, but
Right.
I think it'll help if you like just drew it.
Okay, well, just like we talked yesterday about the Atwood pulley example, so he had one mass here and one mass over here, 2 kilograms each, and he was asking a question to students. I mean, what is the tension in the string? And one common misconception that it would be 4 newtons up. Well, we know that the weight is going to be, you know, each one of these is going to be balanced, right? We're going to have tension up, and it's the same string, so T. And then we have mg for each one. So roughly 2 times 10 or 20, right? So each tension is going to be 20 newtons. It's going to be 20 newtons of tension in the string as opposed to 40 newtons. And he was saying that if it was 40 newtons, then the masses would be accelerating upward. It would just be this strange poltergeist type thing going on. But no, it's 20 newtons of tension. Is that cleared up?
Yep.
Okay, so next time I'll full size it. Maybe we can do a better demonstration or visual on that. So that's the thing that he was trying to show there. All right, so like at this point, let's go to question number 32, if you're looking at your textbook. So we have an object of mass 1 on a frictionless horizontal table. Before that, it's 20 newtons each, because it's 20 newtons because the string is going to have the same amount of force as the weight here. So the weight pulling down on each one of these is 20 newtons. So 2 times 9.8 roughly is 19.6. It's going to be roughly 20 newtons down, and it's going to be equal and opposite to this tension here. Because imagine, if you just throw that out of the way for a second, if you say it's 40 because you want so intuitively to add these, then this would accelerate upward, because this is not going to be 40 ever, right? It's going to be 20. And if this was 40, then this thing flies up. It's going to be a net force upward. That was his, you know, he was trying to clear up that misconception. Okay. Right. So all right, I'll full screen it next time. So sorry about that. But yeah, that's the visual of that. Okay, so if you're looking at your textbook, page 131, number 32, you have an object of mass M1 on a frictionless horizontal table, something like this. Oops. And we got this pulley in space. Weird, but it is what it is. Tension goes this way, and we have our mass 1. Let's call that. And then we have another pulley like so with this extra string, other string. And then we have M2 here. So this is going to be T2, all T2, T1 for this entire string here, and T2 for this string over here. Frictionless horizontal table is connected to an object of mass M2 for a very light pulley P1 and a light fixed pulley P2, as shown in figure 532. If A1 and A2 are the accelerations of M1 and M2 respectively, what is the relation between these accelerations? Now, let's imagine that this pulley here doesn't exist. The distance that M1 would travel would be the same distance of M2 in any ordinary pulley system. If we go back to, say, question 26, the distances will be the same. The accelerations would be the same, the time of motion same, all that would be the same. Now, with this extra pulley, the distance that M1 travels is going to be double the distance of M2. He's going to travel the same distance of M2 this way, and then he's going to travel the same distance going back. So the distance travel is going to be double for M1 than M2. M2 will be distance D, this will be 2D or something. That's intuitive, maybe. And I say maybe because maybe you didn't intuit that. But one way to approach the solution of that, to understand why that works, is to use kinematics relationship. Okay. So we say that A1 and A2 are accelerations of M1 and M2 respectively. Sorry about that. So, yeah. So one thing we can, we notice about M1 is that, the distance traveled is going to be, 1/2 A1 T squared, and that's the distance that M1 travels, and M2, 1/2 A2 T squared. Since we know that M1 travels double the distance, we can take this first equation and multiply it by 2. To x1, and so we multiply both sides by x by 2, and so this will become A1 T squared. Whereas the second mass, his distance is just going to be 1/2 A2 squared. Therefore, the acceleration of A1 is double that of A2 because of this direct relationship. So in answering the first question here, A1 will be double A2. So that's the first part of the question. Any questions there? Issues, comments on why A1 is going to be double the acceleration of A2? So it all goes back to a direct proportionality between the distances and acceleration. Yes.
Sorry, I understand what you're saying. It's just difficult to visualize the way that the pulley works. Is there an easier way to do that?
There could be another way to do it, but
or just an easier way to visualize like how everything is moving.
Yeah, I mean, again, this would have to be better. This would have to be a demonstration to kind of really knock in the visual, because I can say whatever, but until we actually have a demonstration of that, it's kind of tough.
Yeah. Okay. Thank you.
Yeah. I would just go ahead and say, if you look back at question number 26, everything, the distance of both of those masses would be the same distance traveled. But now when you add a second pulley here, the implication from the diagram is that this mass is going to travel double the distance. Although it may be tough to see, but that's the implication from the diagram.
So when you add the second pulley, there are two more tensions, right? T1. So those two T1s are exerting the M1's acceleration, right? So because of T1, M1 goes like twice the distance.
It travels two circuits. It goes first here and then it goes back over here. So that's going to be double the distance that of M2's. M2 is just going to go straight down, whereas M2 is going to go forward and then back. No, not necessarily for the question there. To keep things very, very simple, since you know that mass one, travels double the distance, and you know that distance is proportional to acceleration from this kinematics problem, when you double this, you double this acceleration. So A1 is going, what this says is that A1 is double the acceleration of 2, or A2 is going to be half of the acceleration of 1. So that's why I wrote it that way. So the question was, why is M1 traveling double M2? Well, again, this is outside of actually setting this demonstration up and showing that this actually it travels double this distance. Without the pulley, the distance of M1, the time it takes M1 to travel to the edge of the table will be the same time and distance of M2. They'll have the same accelerations, they'll have the same velocity, same time. But now you introduce this pulley, then the acceleration here is going to be double that of A2 because it travels twice the distance. It goes once and then it comes back twice. So that's what that relationship is showing there. There are certain things, and then this is a generalized question. You ask, sometimes you're just going to have to you're going to take with what you know first. Like if we go back to question number 26. Okay, so the next thing we're going to do is, with any problem, is draw our free body diagrams. We know our perspective pretty much on this guy. So we have the free body diagram on mass 1. So this is going to be tension 1 going forward like so. We have the normal force and the weight. There's no friction. So that's the forces acting on mass 1. And then mass 2. So just to keep in mind, the acceleration of the system It's actually going to go from the wall all the way down. And if we let this mass hang, the system's going to accelerate downward. Okay, so since system accelerates downward, we have negative T2, and this would be M2G there. Then we also have this hanging pulley that seems to complicate our life right now, but it is what it is. We just have to take things as they are. Okay, so then there's T2 on the pulley, which is going to be equal to both of these tensions, T1. So T1 is pulling this mass one here, and this T1 is attached to the wall, and then T2 is just going to be double this tension here. So then, well, that's our free body diagram for this part of T2. T2 will be equal to 2T1.
Mr. Kelly, does this relationship has something to do with the double distance?
No, it's just that T2 is just it's made up of both of those two tensions here. So like if we went back to like question 23, for example, if we made this vertical, if you're going to go there real fast, we can see, we know that in part C that the scale is going to read double the masses, double the weights in 23C. And so that's how we can get this relationship here. It's very similar, except this is horizontal and that's vertical. So that's where that comes from. The T2 is just this double these tensions here. So now taking all of these free body diagrams, negative T2, M2G, T1, acting on mass 1, and then we have this relationship of T2 equaling double the tensions. We can set up our equations of motion. T1 will just be equal to M1 A1, which from before we know that A1 is equal to double A2, so we can just say 2M1 A2. So that's the final form that it equals, because we know A1 is equal to double A2. And we also know that since T2 equals T21, we can say that T2 minus 2T1 equals 0, since they're equal to each other. And also that's negative T2 plus M2G is equal to M2 A2. Two different accelerations. So we have two different equations of motion. Instead of just M2A, M1A, it's going to be M1A1 and M2A2. So just to go back over this. So this system will be accelerating at A1 here. So let me just wipe this out, because this A would incorporate the whole system, and we know it's going to be two different accelerations. So this guy, this mass 2, is moving downward at A2, whereas M1 is moving at A1. So two different accelerations. Otherwise, the other picture is a depiction of the whole of the entire system moving with one common acceleration, and we know it's two accelerations in this case. Okay, so that's the system of equations, two different accelerations. The first thing that I want to do, or it's optional for you, but I want to solve for A2 because the question says to solve for the accelerations and the tensions in terms of M1, M2, and G. So we want to have just those variables in our expression. So taking a look at the third equation, I can substitute T2 for T1 since they're equal, T2 for 2T1. So I can just say, I'm taking a look at this equation and I'm making a substitution. So negative T2 is negative 2T1 plus M2G equals M2A2. And I want to solve for my I'm going to isolate my T1 first, and then I'll get to my A2 expression. So then negative 2T1 is going to be equal to M2A2 minus M2G. So T1 will be M2A2. Let me make a, yeah, so if this is going to be positive, this is going to be negative, and this will be positive. So I just switch the signs. So I can just make this simply positive T1 as opposed to negative T1. So then if I do that, then I switch my signs over here and divide everything by 2. Because that's what we had up top. Since we also know that T1 is equal to 2M1A2 from above, we can then go about our way to get an expression for A2 and then get an expression for A1 and then the tensions. M2G minus M2A2 divided by 2. Multiply both sides by 2 because I want to get rid of this fraction. I'll have 4M1A2 equals M2G minus M2A2. So 4M1A2 plus M2A2 equals M2G. Why did I do that? I want to get all my A2 terms on one side and solve at the end for A2. All right. So I factor out my A2 and I say 4M1 plus 2 equals M2G, and I'm ready to go. So A2 M2G over M1 plus M2. So that's my expression for M2 or for A2 in terms of G, M1, and M2. So if you have any question that asks you to get an expression for something in terms of those variables and you have extra stuff, incorrect. So you have to figure out a way to solve the problem in the terms listed. So that's the expression for A2 from our prior expressions. Okay, 1 second. Scroll up where? Okay, you're gonna have to tell me when to stop. scrolling up could be at the very top. Or where do you need me to go? Don't be shy. We're all in here to, nobody's going to bite you. A little down. Okay. All right. Define little. All right, so now I'm going to get my my A1 expression. Yep. So if I go back to I go back to the first equation, I know that T is equal to M1A1, and M1A1 is actually equal to 2M1A2. We saw that before when the tension in the string is going to be equal to mass times acceleration and the normal force and weight. Yes, they're equal to each other, but they don't mean anything for us. There's no friction in the system, so we don't use it. So now taking this even further, M1A1 is equal to 2M1 and the expression for M2 that we got earlier, which is M2G over 4M1 plus M2. Then A1 is equal to 2M1 M2G over, we divide both sides by M1. When we do that algebraically, it's going to be 4M1 squared plus M1 M2. Does everybody see how I did that part? It's just algebra. I'll do a little middleman operation here. Well, I'll just do the substitution, I suppose. So I divide both sides by my M1. So so then I don't want a fraction over a fraction. So I just multiply by this guy by M1, and this becomes 4M1 squared M1 M2. So this guy goes away, but this gets distributed, multiplied by both terms. So 2M1 2G over, it's my expression for A1. And then the tensions are just very easier. Now that you got your A1s, A2s, you do your back substitutions for T1 and T2. T1 is 2M1A1. You already know what A1 is. So you can just say 2M1 times M2G over 4M1 plus M2. If you want to simplify that, it's just, 2M1 M2G over 4M1 M2. Or just leave it like that, you're fine. Because this was A1. Anybody need to see that? Again, everybody following, tracking? And then T2 is double this, right? Because I got this earlier in the free body diagram that T2 is equal to double this expression. So It's just going to be 4 m1 times the rest. And that's it for 32. Apart from the distance being doubled, I will look back at that again because I'm always interested in making things as easy as possible if there's a different way of thinking about that. But because there's always more than one way to do anything in physics, which is the beauty and maybe even consternation to some. But I'll take another look over that. No worries. But does everybody see this part, T1 and T2? All right, well, we're running low on time for 69, but I'll see how far we can get to it. Does anybody want to see number 69? Okay. So let's go, because I know you mentioned that. Page 135, we have this van accelerating down a hill. A van accelerates down a hill going from rest to 30 meters per second in 6 seconds. During the acceleration, a toy, mass 0.1 kilograms, hangs by a string from the van's ceiling. The acceleration is such that the string remains perpendicular to the ceiling. Determine the angle and the tension in the string. Oops. Okay, so the starts from rest. So the initial velocity is 0. Final 30 meters per second. 6 seconds. And mass of the string 0.1 kilograms. We need to find the angle and we need to find the tension. Forces problem, we have to identify all of the forces acting on the pendulum mass. If we were to set up our free body diagrams, which we're going to do here, we would have 2 unknown variables. If we didn't have, we'd have, not only we would have to solve for tension, we'd have to solve for the acceleration, but luckily for you guys, they give you enough information to solve for the acceleration in the system. And so the only thing that you have to do is solve for the tension and the angle, which you can do from 2 separate equations. So good, we put that all together. So, so first thing we want to do, why are we doing this? To give us information to solve for the acceleration of the system. It starts from rest. It accelerates up to 30 meters per second in 6 seconds. Let's go ahead and solve for the acceleration of the system. The van is moving. So therefore, if we were to, draw the system, just looking at the van separately from the pendulum, the net force in the system is going to be mass times acceleration. And this is before, we're going to draw the forces acting on the pendulum to get the final solution of the problem, which is the angle and the tension. But we know that there is an acceleration based on what the problem tells us. It accelerates down the hill from rest, 30 meters per second in 6 seconds. Let's find this acceleration that should help us for the rest of the problem. Okay, so the first thing we want to do is solve for the acceleration of the van. Final velocity equals initial plus AT, one of our kinematics equations. And acceleration will be equal to VF for t, because VI is 0, that goes away. Six seconds. And so that gives us 5 meters per second squared. Okay, so we have our acceleration. Let's identify all the forces in the system. So this pendulum it's attached to the ceiling by this tension here. It forms an angle theta from top. So we have a component that goes like this and a component that goes like that. So that's going to be, if angle theta is with respect to the vertical, this component here would be t sine of theta. Sorry about that. This guy just comes out of nowhere. All right, so just leave it there for the moment. So that's t sine theta. We also know that the weight of this pendulum points straight down as Fg. Fg equals mg. And there is a component of the force that is going to be pointing in this direction. This angle here is going to be exactly equal to the angle up top. And so this will be, this is Fg here, this component will be mg sine of theta. All right. So what we then have for our equations of motion in the x direction is we have mg sine theta equals mass times acceleration. That's the force, that's the only force in the x direction that's going to be equal to the net force of the system. The van is accelerating down the hill. The acceleration is along the x-axis, positive x-axis. So the acceleration is in the x-axis, and that net force is going to be equal to mg sine of theta. And along the y-axis, the forces are going to be the tension minus mg cosine theta, and that equals 0. There's no acceleration along the y-axis at all. So those are our equations for motion for x and y directions. So now, as you can see, if we didn't have the acceleration, we'd have 3 unknowns, and that would be difficult. Couldn't solve it, but we do have the acceleration here. We can get the angle real quick. Once we get the angle, we can get the tension in the string using the Fy equation. So let's take a look at the Fx. Mg sine theta equals ma. Masses cancel out. And then we have sine theta equals to A over G. We don't want sine theta, we just want theta. So therefore, we do inverse sine of acceleration over gravity. That will give us 9.8. You carry this through, that's going to give you roughly, get you to 30 degrees. That's angle theta. All right, so then using the y equation, t minus mg cosine theta equals 0. tension is equal to mg cosine theta. We're going to have 0.1 kilograms times 9.8 cosine of 30. That gives us roughly 0.84 newtons. That's what we get. You guys just don't like talking, huh? It's got, okay, no worries. You don't have to. It's where I got theta. So, yeah, so I just took the first equation, mg sine theta equals ma. Masses cancel out because both sides equation, da, 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 da. Theta is 30 degrees. Is that all right? All right. Okay, so let's now I'll go to our skills test. Let's get out a sheet of paper there. And what I want us to do, okay, let's see. Let me get the new share here. Yeah, what I'd like you to do is just draw this diagram. So this is a compound Atwood pulley machine. So let's take no more than a couple of minutes to draw it. It doesn't have to be perfect, but you just sketch it real fast, as I'll get to the problem itself. So as you're drawing it, so before I read it, this, okay, so these got this mass over here, but you're going to treat this like another mass, right? So the pulley, this pulley system is actually going to be accelerating downward with one acceleration, okay? That acceleration is going to be A1. So this system as a whole is moving down with acceleration A1. But, in between that, this pulley system has its own individual acceleration A2, because this mass is going to go up and mass 3 is going to come down. It's going to be this A2 is going to be relative to mass 2 and mass 3. But the entire leg of this pulley is accelerating at A1. So just keep that in mind before I go to the description. So, all right, I'm gonna now go to the problem that I'll leave up. So here it is. A compound Atwood machine is constructed by replacing one of the masses of a conventional Atwood machine by the pulley of another Atwood machine. Altogether, there are, sorry, my H doesn't tree, 3 masses, 2 ropes, and 2 pulleys. The ropes and pulleys are to be considered massless and friction-free. Describe the method by which the motions of the masses of this machine can be analyzed. I have to copy and paste my H's, so I apologize for that. So, long story short, I want you to solve for the accelerations of the system, all in terms of M1, M2, M3, and G. You're going to have 3 accelerations, A1, A2, and A3. Why A3? because A3 is going to be a combination of A1 and A2. That's just the entire acceleration. A3 is just the full acceleration of the system. It's going to be a combination of the A1 and the A2s, as if the entire system is moving. So the thing is, what you want to do is get A1, then A2, and then just add them together. I hope you have the sketch. I'll leave this up and ask away as you need it. I'm going to be here after school, so if you need until 2:30, of course I'll give that to you.